project. But before we get there, let me just quickly show you the hardware itself and tell you what is what. So as you know, this is our Node MCU controller over here, and then the two buttons for resetting and booting the Node MCU is over here. Then we have the USB port here, which can be used to program the IC as well as to charge the 18650 cell over here. And then we have the USB to UART converter IC over here, the CP210, which is a USB to UART converter, and nothing much here. Then we have the actual soil moisture design along with its related circuitry over here. And then we have one more charging IC and some protection ICs over here, which I will explain as we get in the schematics. So the schematics is split into different sections. Let's start with the first section over here. I'll zoom into this. This is the controller section. So let's zoom in. So as you can see, the main controller here is the ESP20, which you can see on our board over here. And what we have done is we have connected the RX and TX pin of it to program the controller, and then we are using the GPIO 5 and 4 to power the soil moisture probe over here. So as I told you, the soil moisture, this is a low power design, so we should be able to cut off the power to this entire sensor. So what we are doing is we are using the GPIO 5 and 4 to power the soil moisture sensor. So when we turn this on, the moisture sensor will also turn on. Now then, moving on, we have the whole controller is powered through 3.3 volt through a filter capacitor, and then we have a jumper pin over here, which is actually not needed. It was just for testing. So what you have to do is you have to pull the IO16 pin to high along with the reset pin of the ESP20 to enable it to work in deep sleep mode. So just for testing purposes, I have used a 0 ohm resistor here, but normally you would have to pull this pin to 3.3 volt using a pull up resistor for enabling it to work in deep sleep mode along with the reset pin. And then we have the GPIO 0 to enable and reset pin pulled up to 3.3 volt using a 12k pull up resistor, and then we have the GPIO 15 pull down using a 12k pull down resistor, and again there is a filter capacitor between the reset pin and the ground. So moving on, we also have these two buttons which I showed you earlier, the reset and the boot button, which is normally used for programming our ESP20 and resetting it to actually program it and to actually put it in programming mode and working mode. Moving on to the next section, we have our soil sensor. So what actually happens here is that this circuitry you see here is present on the board over here. So what actually happens is as soon as you turn these GPIO pin on, current starts flowing through these two probes over here. So the reason why we have used two GPIO pins to power it is that the maximum current that a GPIO pin of your ESP20 can provide is 25 milliamps. So since we are using two GPIO pins, we should be able to source around 50 milliamps from your GPIO pins, which should be enough for our moisture sensor to work. Now how the moisture sensor works is that once you turn it on, your current will start flowing through this, and then it will come to your current limiting resistor over here, which is a 100 ohm resistor, and then it will go to your probe 2. So this pad you see here is the probe 2, and as we know, it will be buried inside the soil. And what happens is when it is inside the soil, based on the amount of moisture present in the soil, the current here will reach this second probe, which you can see over here. So the second probe is over here. So what happens is the current from here, based on the moisture content present in the soil, it will reach to the base pin of this transistor. So when it reaches here, the transistor might fully open or partially open, telling us how much moisture is present in the soil. If the soil has very good moisture, then the current will easily flow and turn this transistor completely on, and the signal pin over here is connected to the ADC pin on our controller, and we'll be able to read the complete GPIO voltage on this pin. So yeah, based on the amount of moisture present in the soil, the transistor will either fully turn on or partially turn on or fully turn off, and by reading the status of the transistor from the signal pin over here, we'll be able to tell how much moisture is present in the soil. Now, how these pads are designed on the PCB, well, I'm not going to explain that. I'm just going to drop a link to a SparkFun page. So the complete design along with the pad, they have also provided an Eagle design file. Everything is properly provided and explained by SparkFun. We have just reused it for our purpose over here. I'm not going to spend time in explaining that because there is no point reinventing the wheel. And then moving on, we have our USB to UART section over here. So normally we have two options here. One, to program this Node MCU, we could have used an external FTDI board to just connect the RxTX pin ground and program this IC. But we used a CP210 programmer IC on the board itself, mainly for two reasons. One, you will no longer need to press your boot button and reset button every time when you're programming your ESP2LE. You can just upload the code directly and it will automatically be switched from programming mode and operating mode. Second thing, when you plug in this, you will also be able to use the serial monitor, so you can actually store the data in EEPROM and read it to monitor what was happening with your device. You can get the past history of soil moisture and stuff like that. So we thought we will add a USB to UART controller on the board itself. So how it works is that another important thing here is the jumper pin over here, which you can see over here on the board. So what we have done is we have added a jumper pin so that when you don't want this USB to UART section to work, there's no point wasting power in powering this IC. So you can just remove this jumper pin and this whole IC will be disabled and will no longer be powered. So the 3.3 volt from here goes through the jumper, and then we use a label called CP210 to power, which is used to power this entire circuitry over here. So on the right side, you can see all the UART related peripherals, UART related terminals like RX, TX, RTS and DTR. We also have reset and suspend pin, which is just pulled high over here. And then here we have two filter capacitors along with VBus, which is the actual 5 volt coming from your USB connector over here. And then you have your USB DP and USB DN, which are the data pins from your USB controller. So that's it, nothing much here. On the downside, you have one more interesting setup with 2 transistors and 2 resistors, which is actually used to automatically configure your ESP2LE. So using this setup, you will just have to upload the code from your Arduino IDE. Our ESP2LE will automatically be put in programming mode, and after the code is uploaded, it will automatically be taken out of programming mode and it will start working as if you just resetted the controller. So yeah, this is a useful setup, especially when you're developing your code. And then moving on, we have our USB section here, which you can see over here. We just have the USB connector itself along with a diode D1, which is on the board over here. So the diode D1 is actually used for ESD protection. The part number is SRV05. So the diode actually, the package actually comes with 4 diodes inside. I have used only 3. One is connected to USB DP, USB DN, and the VBus itself. 1 diode is left free. And then here we have a small setup which will turn on the LED whenever the USB connector is plugged in, just to make sure that we are actually getting power from the USB connector. So yeah, just a resistor with a current limiting diode. Moving on, we have an interesting IC here, which is used to charge our 18650 cell over here. So this IC is from Analog Devices and it is called LTC4054. We have been using it extensively for a lot of projects here. So what basically happens is this VBus is the voltage that comes out of this USB connector, and it is used to power this IC. And this resistor over here can be used to set the output charging current using the formula charging current is equal to 1000 volts divided by the value of the resistor. Here we have used 1.25K. So based on that, our charging current would be 800 milliamps, which is the maximum charging current for this IC, but you can configure it in any way you want. Then we have an interesting pin called the charge pin, which will indicate whether the IC is charging the cell or not. So we just have to connect an LED, and this pin will go low whenever the IC is charging the cell. So we'll see this LED turn on. Once the charging process is complete, it will go high, and hence the LED here will also turn off. Then we have the actual voltage which is used to charge the cell. We have labeled it charger. We will be connecting is to our 18650 cell in the next section. And so basically what the cell does is that it senses the charging current and it supplies the charging current through this BAT pin, and it monitors the charging current. Once the battery gets charged, the charging current will start falling down. You can see a neat graph in its data sheet, and when the charging current falls down a particular value, the cell will disconnect the battery from the voltage, and it will no longer charge your 18650 cell. So that's it. This is how the cell works. It's very useful when you are using your 18650 cells to power your projects. And then moving on, we have our last section, which is the voltage regulator section. Now what this voltage regulator does is that from the battery, which you can see here, it takes in the variable voltage, which will normally be 3.4 to 4.2 volts, and it will regulate it to 3.3 volts. Now normally we'll use an AMS 1117 3.3 volt to regulate your 3.3 volts as an output, but here we have used an LDO regulator, which stands for low dropout voltage. Basically what it does is that it makes sure that the energy from this cell is converted to 3.3 volt without much loss, meaning there won't be much voltage drop across the IC itself. This is very important because we have to save every bit of juice that we can probably get out of this cell. So yeah, that's it. We just have some output filter capacitors, and then over here you can see the charger pin, which I told you earlier from our charging IC. So this charge pin is connected to the positive terminal of a battery through a reverse current protection diode, and then over here you can see the reverse polarity protection circuit. So basically we'll use a Schottky diode for reverse polarity protection, but in that case, again, the current has to flow through the Schottky diode, and there will be a huge voltage drop across it, and we will lose energy from our cell. So we have used a P-channel MOSFET. This is a very interesting circuit. We have already covered this previously. You can check on Circuit Digest. This circuit is a lot more efficient than using a Schottky diode. So basically what happens is this P-channel MOSFET here will turn on only when the cell is connected in the reverse polarity. If you connect it in the other way, the MOSFET will open, and hence there will be no output going out of the cell. So that is it. We regulate our 3.3 volts here, and then this 3.3 volt is what we have been using to power our ESP, to power our USB to UART converter. So the whole schematics here is actually powered from this 3.3 volt cell. So that is it, guys. This is how the